So, operational amplifier can do many mathematical operations. That's the reason actually it is called operational amplifier, OpAmp. So now let me talk about some of those mathematical operations that you can perform with OpAmp. So the first is uh, current to voltage converter. You can convert current to voltage. So in many applications you're going to need that. So you will get current from some sensor, say, and you will have to convert that um, current from this different sensors to the voltage, right? And then you can calibrate the instrument. So if you connect, you just need a resistor. So you apply the input current to the to the inverting input, and you need a feedback resistor like that. And then if you connect like this, so it works as current to voltage converter. So how you show that? So first of all, at KCL, right? If you apply KCL at this junction, so it's going to give you this, the input current plus this feedback current is equal to 0. That will give you the input current is negative IR. But since this V plus is 0, V plus is grounded, right? So that will make V minus also 0 at put at virtual ground, right? That will force V minus to stay at virtual ground because they are equal. So then IR will be, right? So I'm just going to show you here. IR, which is the feedback current, is V out minus V in, V negative, divided by R. But this is 0, so that's why you get that. And therefore, then you substitute the value of this to this, right? And then you can clearly see the output voltage. Output voltage is directly proportional to the input current, right? So it works as the current to voltage converter. Okay. Now next application is mathematical operation is differential amplifier. So you can configure op-amps in such a way that it works as a differential amplifier. So whatever output you get is the difference between these two terminals. So that's why it is called differential. You can also call subtractor. So let me show you some math here. So the mathematics is done here already. So I'll just, so you need two voltage divider here. So one is for the inverting input, the other one is for, other voltage divider is for the V plus in non-inverting input. So then you apply those two voltages to be subtracted at V plus and V minus like this, and let's see what would be the output. So let me quickly show you this with the same circuit. So for example, first of all, I'm gonna apply KCL at V minus right here. So that's gonna give you V2 minus V negative divided by R2, right? V out minus V negative plus divided by R1 is equal to 0. So I just apply KCL at this node, right? That's going to give you this. So let's try to solve for the output or V negative from here. So V2 over R2 minus V negative is 0, and let's see, so V2 over R2 plus V out divided by R1 is equal to V negative is common factor 1 over R2 plus R1, right? And so this is going to be R1 plus R2, R1, R2, right? And V negative is R1, R2 divided by R1 plus R2 times this. right? Let's say equation number 1. And again apply KCL at V plus right here. So do the same math. So you have V1 minus V plus divided by R2, right? No, I'm sorry, you don't need to do KCL here. So you just use the voltage divider. I'm sorry. So so V plus is just this. V plus is just from the voltage divider. Is V plus is just the voltage across R1. So just using voltage divider is R1 over R1 plus R2 times whatever voltage you're inputting, V1. That's just using voltage divider. Okay. So let's call equation number 2. And our OpAmp rule says V plus is equal to V minus. They have to be equal. So these two equations are equal. So equate them. So and then solve for so I'm just equating those. So this will cancel out, R1 will cancel out, right? And I'm solving for V out somehow. I'm solving for V out. So you still have R2 here. So R2 V2 over R2 plus R2 over R1 times V out is V1. And this will cancel out. So so R2 over R1 V out is equal to V1 minus V2, right? So then V out is V1 minus V2 times R1 over R2. So you can clearly see the output in this configuration. Output at the OpAmp is just the difference between the input voltage, difference between these two input voltages. So that's why it is called differential amplifier. Okay, so that's why it is called differential amplifier. Now next, you can use the same OpAmp as a summing amplifier. So you can use it as an adder, so which you need in many computation. So let me quickly show you how to use this OpAmp as an adder to add two voltages. So to use that, you have to configure the OpAmp in this configuration. Okay, so you do need a negative feedback to the inverting input with this resistor R1, and you're applying both voltages V1 and V2 input voltages through these two resistors at the same node. So then let's figure out the output. Okay, so output, so then you just apply KCL at V negative right here. So this is going to be I1 plus I2 plus I3 is 0. I1 is V1 minus V negative divided by R2, right? Plus I2 is V2 minus V negative divided by R2. So these two resistors must be same if you want to configure this as an adder. Plus I3 is V out minus V negative divided by R1. So all sum equal to 0, right? But since V positive is connected to the ground, right, this will force to stay V minus at virtual ground. So V minus is also equal to ground. So V minus is at virtual ground. So that makes it V1 over R2, because these are all V minus is 0. 0. So remember, we're calculating V out. So V1 plus V2 over R2 is equal to negative V over R1. So V out is negative R1 over R2 V1 plus V2. Okay, so this is the output from this configuration. So you can clearly see in this configuration this op-amp works as an adder but inverting. So the output signal will be inverted by 180 degree out of phase. Okay, that's why it is called inverting summing amplifier. Yeah, these are also here written here. So the next application is next mathematical operation of op-amp is an integrator. So you can use the same op-amp as an integrator. Okay, so if you want to use the op-amp as an integrator, you have to connect the circuit like this. You need a capacitor as a feedback circuit, and you apply input to the inverting input through a resistor like that. And again, this is at virtual ground, so V plus is connected to the ground. So again, KCL, if you apply KCL at V0, so the sum of the total current is 0. IC is negative VR, but IR IR is VI, input signal divided by V, because this will give you this, but VI is at 0, that's why you get this. So we assume that charge is 0 at t is 0. So initially the capacitor is empty. Let's assume that. So the voltage output then will be charge divided by capacitance, because why? Q is CV. That's why. Right, and this is what. So charge is then the integration of the total current, right? Charge is the integration of the total current over the time t. And then, but IC is given by this. So you can clearly see the output is proportional to the integration of the input signal. Since output is V out is proportional, right, to the integration of the input signal. So that's why this configuration of op-amp is called integrator, because it simply integrates whatever signal you feed to the input. So as an example, if you feed a square wave signal, the output will be this triangular wave, because the integration of this, right, which is the area under the curve, it will be this triangular wave, as an example. Okay, the next mathematical operation is differentiator. The same op-amp can also be used as a differentiator. Okay, that means the output will be just the derivative of the input signal. So for the differentiator, you just need to configure like this. So just switch compared to the integrator, you just need to switch the capacitor and resistor like this. So your the negative feedback is drawn through the resistor instead of capacitor. So then do the same thing again, exactly same. So input, well, since V negative is at virtual ground, because V positive is grounded, right? So that makes your input voltage is just the capacitor voltage, right? Because this is at 0 volt, this is at virtual ground 0 volt. So VI is just the voltage across the capacitor, and voltage across capacitor is 1 over C, because voltage across capacitor is Q over C, and Q is the integration of the capacitor current from 0 to the full period, plus some integration constant. Okay, and then this is VI, right? And then just differentiate both sides with respect to time. So that's going to give you dV over dt, and this whole thing is going to give you the total current, right? The integration of this the integration of this is just IC over C, and substituting the value of IC gives you this, because IC is, remember from previous part, IC is just negative V over R. Okay, right, and then just put it there. You can clearly see, right, output is proportional to the derivative of the input voltage, so that's why it is called differentiator, because output